Good morning, everyone. We have discussed one type of randomness that you encounter while doing IC design. That is just the random variation in the component values. Okay. Now, because it is random, you can only describe it by some statistical measures, and that we saw how to do. Okay. So the random variation, the small variations in a component value can be converted into some small signal source, and you can do the analysis and find the output. Now you can relate the variance of the output to variance of the component value. Okay. And the variance of the component value is related to the size. That also you know. Okay. Now it turns out that even if there were no random variation in the component values at all, so let's say we again start with the example of a resistor where a voltage V is applied to a resistance R0, and you make 1,000,000 copies of this and find the current. Let's say you are able to measure the instantaneous current. So there are lots of instances of this. V0 and R0 have exactly the same values in every copy. Let's say you do this experiment. You would expect a current that is, if I call this V0 by R0 in every case. Okay. This, x-axis is time, yes. I apply a constant voltage, I expect a constant current. Okay. And the current depends on the resistance value. But if you are able to measure the instantaneous current, okay, with however you do it, you will find that the current is something like this. Okay. It will vary around the value that you expect. Okay. And the variation will be random. I'll explain what I mean by that. But it will be different at different instants of time. And it will also be different for different examples that you take. Let's say you make 1,000 copies of this and measure the current at some particular instant in all of them. They will also be all be different from each other. Okay. So this randomness, why do we see something like this? Why does this happen? Huh? There is no nonlinearity here. What is nonlinearity? So what is current? It's a flow of electron. It basically denotes the rate of flow of charges. So let's say this is your resistor, and you cut a cross section here. Okay. And let's say you're able to count the number of electrons that cross this surface, that you can relate to the current. Now it turns out electrons are not crossing in some nice pattern at a uniform rate, but they'll be buzzing crazily back and forth. Okay. So it's like electrons will be going back and forth around this, but on average, they'll be drifting to one side. Okay. By the way, this it turns out it will be there even if there is no current. Okay. That is, if V0 is 0, then you expect that no electrons cross this barrier, but that's not what happens. They'll be crossing it, but on average equally in both directions. Okay. So this happens because of random thermal motion of electrons. Okay. So you expect it to be related to temperature, and it is, as we will see from the expressions later. Okay. So because of this, on average, of course, the mass, you can think of it as, you may have seen this in physics textbooks. if you look at the drift velocity, what is the drift velocity in conductors and so on? I mean, you may have solved some physics problems. Huh? No, not the formula. What is the value? Something very slow, actually. I mean, it's not related to if you apply a voltage, the current immediately starts flowing, but it doesn't mean that the electron immediately jumps from here to there. So that thing is quite slow, but this thermal motion is fast. So the picture is like you have a mass of buzzing bees which are slowly drifting in one direction. Okay. So now because of this, instantly if you measure how many electrons are crossing this and calculate the current, you will have values above and below the average current that you expect from Ohm's law. Okay. And this in particular in a resistor, this is called thermal noise. This is random motion of electrons due to their thermal energy. Okay. So now this part, the instantaneous current minus the current that you expect from Ohm's law, this is basically the noise current. Okay. So essentially it is if I simply move this down to 0, so that is the noise part. You have the current because of the element relationship, plus you have this current because of random motion. The two are analyzed separately. Okay. So now this part is noise. I have done it for one example. The same holds for everything. Okay. Now in resistors, it turns out that this noise is independent of how much current is actually flowing through it. Okay. That is, you can have 0 volts across it or 10 volt across it. The noise part will be the same. Okay. So that is some property of resistor's noise. So now we need to find a way of analyzing this. Okay. This random noise. It varies with time, and it's also turns out to be uncorrelated in different instances of the resistor. Okay. That is, if you look at a particular instant here and take samples of the noise, right, they'll all be uncorrelated from each other. Now, we have an additional complication compared to before. How do we describe these random quantities? We can describe the probability density function or the cumulative distribution function. Okay. And from that, we can extract measures like mean and variance and so on. Okay. Now, there is this additional element of time. Okay. Because this, what you get at this particular time instant is different from what you get at another time instant and so on. Okay. So basically, in general case, you will have to describe, let me just use the probability density function, but equivalently you could use the CDF, the cumulative distribution function also. This PIN stands for the probability density function of the noise current IN. Okay. So in general, it can be a function of time. How many of you have taken courses in probability and random processes? Okay. So now, thankfully, it turns out in most of the cases, we don't have to worry about that. There is a set of processes called stationary processes for which the probability density function is independent of time. Okay. Of course, it doesn't mean you will get the same values at every time. It just means that the probability density function is the same at all times. Okay. And it turns out the resistor noise is one of those cases which is stationary. This probability density function is abbreviated as PDF. This is constant with time. Now there are some details. Again, those of you who have taken classes on random processes know that there are stationary processes and there are wide sense stationary processes and so on. What's the difference? There is something called wide sense stationary. So now from the probability density function, you can calculate the mean and variance and higher order moments and so on. Okay. Wide sense stationary means that only the mean and variance are constant with time, but it doesn't mean that probability density function itself is constant with time. Again, we don't have to, it turns out, worry about it. First of all, the probability density function we get, just like for random mismatch, this is PDF of this noise. This is Gaussian. Okay. So the probability density function of noise will be Gaussian. And by definition, it will be zero mean, because whatever current we get because of applying the voltage, that we treat separately. We are only treating this extra part, which by definition has a zero mean. Okay. Also, if it is Gaussian, it means that wide sense stationary implies stationary. Okay. For Gaussian processes. So again, we don't have to worry about it. So now, what is it? If it has zero mean, so what is the one thing that is left to calculate here? Variance. So variance will be constant with time for this. Okay. So we will have to be able to calculate the variance, right? Is this okay? So that's what we'll have to do. We'll come to that. This is just information. We won't refer to it further. Now, the basic challenge is that we have a signal that is time varying as well. Okay. And it's also random, and we have to make calculations on that, right? So we will go back to deterministic signals and then relate it to how we do things for deterministic signals. Okay. So first of all, what is the analysis method that we prefer, that we use when we have deterministic signals but that vary with time? How do we usually analyze that? What do we do? I have a circuit with resistors, capacitors, all kinds of components, and I have a sinusoidal signal. What's the method you would use to analyze? As opposed to when you have a DC voltage. What's the difference? Huh? Basically, you use frequency domain analysis, right? Why? Why do you use frequency domain when the signal is time varying? No, but what is it about analysis that, yeah, why is it easier? No, you have to think about the phase. That's all you think about, right? Yeah. So the different, instead of solving differential equations, you solve algebraic equations. That's why you use frequency domain analysis, right? So now, because this is now noise is time varying, see earlier also we dealt with randomness. Then we didn't have to worry about all this. We just had to do the analysis for the signal. And after that, this variance stuff was just very straightforward. Okay. Here, by the way, that in mismatch also, if you are looking at time varying signals, that mismatch, the small signal source corresponding to mismatch error could be time varying. But anyway, now we need frequency domain description of these random signals so that we can go forward with the calculations. Okay. Any questions here? So for that, we'll revisit how we describe deterministic signals in the frequency domain, and from that extend it to random signals. Okay. So again, our goal here is not to explore theory of random processes in any detail, but to know just enough to go ahead with our circuit calculations. Okay. Now, before I go there, even this is something that you know. So we have signals of let's say different wave shapes and so on. Okay. And there are metrics that describe the signals. Okay. It could be the peak value or the peak to peak or the root mean square value or the mean squared value and so on. Okay. Now, of course, these are all I've drawn examples of a sine wave, a triangular wave, and a square wave. Now we have random signals. Okay. Which of these measures is suitable for describing random signals, do you think? First of all, mean square or RMS is just the square root of that. Either one is fine. Why not peak or peak to peak? Random. So what is the issue? No, in every one of them there is lots of information because you are using one number to describe a signal that is varying in time. Okay. What is the peak to peak value of a Gaussian? Infinity. So it's basically useless, right? So you describe it with the Gaussian signal can be as high as infinity in principle, right? So we describe it with RMS or mean squared, and it also makes, I mean, they all say something about the signal, but this RMS or mean squared, if signals have the same mean squared value, then, and if you apply that voltage to a resistor, then the resistor will heat up by the same extent. That's the idea, right? And by the way, when we say power of a signal without referring to any resistor and so on, this means the mean squared value. Okay. Right. When, I mean, even during when we do analysis with signals and block diagrams where there is no circuit and no power dissipation, we still refer to power of the signals. What is meant is the mean squared value. Okay. So that's what we'll try to calculate, mean squared value of noise or something. Okay. Now to do that, let's revisit frequency domain representation of deterministic signals. Okay. We'll start with deterministic signals. So let's say you have a time domain signal. In the time domain, it is x of t. Okay. So what frequency domain description would you use? What is it? No, what is it called? What is the Fourier transform? Let's say. Okay. So now it's Fourier transform x of f is x of t exponential okay. So you can calculate this, and of course you can do calculations in the Fourier domain, which is easier in many cases, and then come back to the time domain by inverting the Fourier transform. Okay. So if x of t and x of f are a Fourier transform pair, which is indicated by the script f, then x of t you can get by, what is x of f really? What does x of f represent? What is it? You have to increase the amplitude for me to hear the signal. Yeah. So it basically this represents some amount of signal, let's say, that lies around this frequency f in a band delta f. So basically x of t is summing this thing. X of f delta f represents a signal, a complex exponential of frequency f. So if you sum over all frequencies, you will get the time domain signal. Okay. Of course, we usually don't directly use these formulas to calculate, that you would have done in the first Fourier transform course. After that, you know the Fourier transform for some standard signals and you go with that. But now, can we use it for every signal? Is there are there some terms and conditions that limit you from? Huh? It should be absolutely integrable. Basically, it should have finite energy, right? So this is applicable only for finite energy signals, which are many times simply called energy signals, right? Okay. So that means that that has to be satisfied. Now let me go to signals that don't follow this, but before that, let's see some other related measures. Earlier, we said that we have to now deal with random signals, right? And in case of random signals, the exact waveform is not known. Anyway, you can't tell, right? So you have to measure it in terms of its power or energy and so on. Okay. So now, in these signals, there are measures that relate the energy. What are they? I mean, in the Fourier transform also. What is it? Yeah, what is autocorrelation function? What is the, all of you know about the autocorrelation function? What is it? So, autocorrelation function is x of t minus tau or t plus tau, it doesn't matter. And this will be a function of this time shift tau. Okay. So first of all, this Rx versus tau, it is going to be symmetrical, right? Because if you just replace t with tau, I mean, substitute some variables, you will get that this is an even function. So it will vary in some way like that. Okay. What is this value? What is that? It is this is the energy of the signal, which is the same as that, right? Because if you substitute tau equal to 0, you just get integral of x square. Okay. So now, and what is the Fourier transform of this? If you don't remember this, these things, please go and refresh your Fourier transform basics. What is the Fourier transform of this? What is it? Yeah, what is the expression for it? What is the Fourier transform of the autocorrelation signal? It is, again, I think, when did you learn about Fourier transform? Only in signals and systems or in other courses also later? In which courses did you learn about the Fourier transform? Signals and systems only. Okay. So please go and refresh these things. So this autocorrelation function is related to this by the Fourier transform. Now, some properties of Fourier transform you need to know to be able to do calculations quickly. Now, in general, if you have any Fourier transform pair, so let's say this one, what is the integral of the Fourier transform? It is, right? It's the value at 0. So similarly, because these two are a Fourier transform pair, integral of what is this? This is the autocorrelation at 0 time shift, which is what? Energy. So now this you can see, what does this represent in that case? Absolute value of x of f square. It's the energy. I don't know why you are suddenly jumping to power. It's still the energy. It's the distribution of energy over frequencies, right? So if you integrate this over all frequencies, you will get the energy. So you can call this energy spectral density. Okay. So these things I think you already know, and if you have forgotten, please go and refresh them. Okay. So these things you should be somewhat fluent with. The basics of Fourier transform of some sort of popular signals, and then basic properties like integrating the Fourier transform over all frequencies will give you the value at 0 and so on. By the way, this is a symmetrical relationship, right? With the exception of this, you have a minus here and a plus there. So whatever relations hold in going from time to frequency will hold also in the other direction with some minor changes. Okay. And you also, yeah. So basically, the autocorrelation function will be symmetrical. What does it say about the Fourier transform? If a signal is symmetric, it will be real, right? So, and obviously, this absolute value of x of square is by definition real. Okay. And the energy is also real. So, this is energy spectral density, and this is energy of the signal. Okay. So, for random signals, this may be a more useful way. Describe the energy instead of instantaneous value and so on. Okay. But we had this caveat, this Fourier transform was applicable only to some class of signals. Okay. Now, what is the signal that you normally see, or what is normally taken as examples in classes like this? Sinusoid. What did you say? Unit step. Okay. Yeah, we'll not worry about the unit step now. Let's look at the sinusoid. It's a horrible sinusoid, but anyway, what is the energy of this? What is the energy of the sinusoid? Infinite. Okay. So all the stuff that we have so far is useless. It doesn't work, right? So we have to, this is called a power signal, which has a finite power, which means, I mean, non-zero power means infinite energy. Okay. And in fact, the random signals are also like that. They'll last forever, right? Any signal that persists sort of forever is has infinite energy. Okay. So we have to find, first of all, different measures. The Fourier transform stuff is useful, but we have to, that's not directly applicable to power signals. So we have to do something for power signal. Okay. So there is a handout in the course page. I don't know if you have seen that. something related to spectra and so on. So please go through that. Again, our objective here is purely utilitarian treatment. We are not going deeply into the theory. We do just enough to get on with our calculations. So what is it that is done for power signals? So here you modify the definitions slightly. Okay. So earlier we had now this clearly diverges. This integral diverges for the kind of power signals that we want to deal with. Okay. So we define something that looks similar, and in fact it's related. So let's say I define this over a window of width t. Okay. And then take the average. I divide it by t. Now you expect that because you are dividing it by t, this will converge. Okay. And that is exactly what happens. So now we define, by the way, yeah, similarly, so this by itself we will not use. I will show you what it's useful for. And earlier, we defined the energy autocorrelation function. Okay. Now we will modify it for power signals. I will still use the same symbols in order to avoid complexity of notation. Anyway, we'll be using only this from here onwards. And as with Fourier transform, most of the time after learning the basic definitions, you never directly calculate the Fourier transform, right? You have some known results and you combine them in whatever way you want. So you calculate this over some finite window. And you take the limit t going to infinity. Okay. So this and for a periodic signal, you will get the same result if t is some integer number of the periods, right? That part is also clear. So now what is Rx of 0? Imagine a sinusoid. What is this? It is power, right? It's the power in the signal. It's basically the mean square value, right? As I mentioned earlier, if we are not referring to circuits and so on, power simply means the mean squared value of the signal. Okay. Sorry, I should not have put 1 by t here. So we'll just take a, it's just taken for a finite window. Okay. It's just the Fourier transform, but defined over a finite window. Okay. So now this Rx of tau, what is the Fourier transform of this? Earlier, for the energy signal, the Fourier transform of this was that one. Okay. Now it turns out for the power signal, okay, it is okay. So you take that sort of pseudo Fourier transform over that finite window and you take the absolute value square divided by t, you will again get a finite result. Okay. Is this fine? So earlier I had mistakenly put a 1 by t here also. That's not correct. So basically, the 1 by t should appear there. Okay. So now you can see these definitions are all very similar. Okay. And this is usually defined, usually denoted by Sx. And what would this mean now? What was this actually? What was the interpretation of this signal, this function? It's the energy spectral density. That is how the energy is distributed across frequency. So analogously, what would this be? Sx? It's the power spectral density. Okay. I could have given you all these and just told you to use the formula, but it's useful to connect it to something that you already know. Okay. So now Rx of 0 is the power signal and integrating Sx over all frequencies will give you the autocorrelation at 0 time shift, which is the power or the mean squared value. Okay. Is this fine? Any questions? So we have tweaked the Fourier transform definitions that you know very well to make it applicable to power signals. Okay. So instead of energy, we'll be calculating power. We have the energy autocorrelation function and its Fourier transform. If you integrate that Fourier transform at all frequencies, you will get autocorrelation at 0 shift, which is the energy. So here you will have the power spectral density and for autocorrelation, the power autocorrelation function are the Fourier transform pair. So if you integrate the power spectral density over all frequencies, you will get the power autocorrelation at 0 shift, which is the power of the signal. Okay. So this is eventually what we'll have to calculate. But so far I have not said anything about random signals. I will come to that. Okay. Any questions so far? So now just to give some examples and give a better feel for this. So let's say we have Vp cos 2 pi f naught t. So first let's take to the classical Fourier transform. What's the Fourier transform of this? What is it? What does it consist of? The Fourier transform of this? Impulses at f naught and minus f naught. Okay. And how do you describe the size of this impulse? Yeah, what is it? This is Vp by 2, but what is Vp by 2 actually? What area does it, what does it denote? It denotes the area of this impulse. Okay. And another example, let's say Vp exponential j 2 pi f naught t. What is the Fourier transform of this? You will have an impulse only at f naught and its area would be Vp. Okay. So this is just the Fourier transform. Now let's do the power spectral density. You can't calculate the energy spectral density of a sinusoid, right? That diverges. So we have to do it for power. So again, I have Vp cos 2 pi f naught t. What do you think is the power spectral density of this? If it's easier, we can do the exponential first. What is the power spectral density of one of these? Vp exponential j 2 pi f naught t. What do you think is the power spectral density? What will it consist of? Impulses. That you guess, because the sinusoid has only those frequency components, right? So Vp exponential j 2 pi f naught t, where will be the impulse? At f naught. Okay. And what will be the area of that impulse? Why Vp square by 2? What is the power of that signal? Says Vp square. Okay. This is Vp square. What about that sinusoid Vp cos 2 pi f naught t? Where will it have non-zero values? F naught and minus f naught. Okay. And what will be, you will have impulses at f naught and minus f naught. What's the area of these impulses? How much? Vp by 2. Why did it become Vp? Vp square by 4. Yeah. So again, this type of stuff you have to do. Okay, you know, already know the energy of the signal. That for that you don't need to go through this frequency domain calculations and so on. What is the energy of this? What's the power of the signal? Power or the mean square value, it is Vp square by 2, and it's equally distributed between the impulses at f naught and minus f naught. Okay, so you have Vp square by 4 at on each side. Okay, so this is the power spectral density of a sinusoid, and it doesn't matter whether it's cos or sine, because for the Fourier transform it matters, but for the power spectral density it doesn't matter. Whether you have cos, sine or any other phase, you will have the same power spectral density. Okay. It's the same answer for that. Okay. Now this type of representation is common in some areas, but basically where the frequency axis runs from minus infinity to infinity. Okay. Now what is the property of real signals for the Fourier transform magnitude or the power spectral density? It will be symmetric, right? The negative part will be the same as the positive part. So because of that, in many areas it is common to have only one side shown. Okay, it's called the one-sided power spectral density. Now there is no way we can go back and change in time. If everybody used only one notation, it would be easy, but that's not the case. Usually in communications, two-sided stuff is very common, and in circuits, one-sided stuff is very common in some areas. Now those of you who are taking advanced electrical networks, in that maybe the two-sided stuff is easier, because when you have frequency conversion and so on. So you eventually have to get used to both, and there is no big deal other than confusion. So basically these are two-sided spectral densities. By the way, I gave this example, but this is a complex signal. This is not what I'm talking about. The real for real signals, it will be symmetric. For complex signals, you have to show the whole thing anyway. Okay, on both negative and positive frequency axis. So for a real signal, you could get away with showing only one side of it. This is two-sided PSD, and for the same sinusoid, you could also have any phase. if you have, if you want to show one-sided power spectral density, what would it be? You will have a component only at F naught, and what will be the area? Vp square by how much? It will be Vp square by 2. If you integrate the one-sided spectral density or two-sided spectral density, you should get the power. Okay. So in that sense, they're consistent. So one-sided, it's not just you show one half of it. Okay. If you integrate it, then you will get Vp square by 4, right? So whether you integrate one-sided spectral density from minus infinity to infinity or two-sided spectral density, you should get the same answer. Okay. So that's why you show only one side of it, but double all the components. That's all that's there to. Okay, because it's symmetric after all. So you can think of it as folding and adding. Is this fine? So this one-sided PSD is what we will use for describing our noise sources also. Okay. So eventually you will have to do calculations with this one-sided PSD. But of course, if you had occasion to use two-sided PSD, that's also easy. Okay. Any questions here? So please go through that handout and refresh the basics of Fourier transform and so on. And also, I think there is a handout on Laplace and Fourier transform. Those things you already know from signals and systems, but please go and refresh the basics nonetheless. Okay. Now, all this is for deterministic signals. I started off by saying we have noise, which is random. We'll have to be able to deal with that. Okay. But how do we do that? Because the problem with noise is, I mean, you have 1,000 instances, every instance of it is different. Okay. So what is it that we have to, do? Yeah. So let me ask you something else. So let's say I asked you to basically collect data on throwing of a dice or something, some random stuff. So I say that you get 1,000 people and give them each a die and ask them to throw, take the data, give me the statistics. Okay. And I'll say that for every person you hire, I'll give you 100 rupees. What will you do? What is it? You figure out the scam immediately, right? You will do it 1,000 times and pocket all the money. Okay. So this is intuitively satisfying. You intuitively feel that, hey, who cares about 1,000 people? If I do it 1,000 times or I give it to 1,000 people, I get the same result. And it turns out that this is true, not universally, but in many conditions. And for coin toss, you feel this, it appears to be obviously true, right? I mean, how does it matter if 1,000 people throw it simultaneously or I throw the same coin 1,000 times? Okay. And this property is called ergodicity. Have you heard of this? Ergodic processes. So basically, this means that you average over the ensemble. Ensemble means collection of different instances. That is, like you have different people and you collect statistics from many, versus you calculate averages over time, you get the same result. Again, this is not a universal property, but it holds for what we want to calculate. So it's fine. Okay. So again, let's go back to random noise. So I have all these instances. Again, I'll plot the current. So I'll show only the noise part of it. So noise in one resistor could be like that, and noise in another one will be something different. Okay. In general, I mean, I'll represent this as x1 of t, x2 of t, xn of t, and so on. Okay. Now, one is, if I know the waveform x1, I can treat it as a known time domain signal and calculate whatever I used to calculate for time domain signals, right? Fourier transform, power spectral density, all that stuff. Okay. So let's say I do that. I calculate I calculate the power autocorrelation of x1, which is This is not periodic, so I have to take that limit t going to infinity. Okay. And from this, I could calculate the power spectral density according to my previous definition. This is the Fourier transform. Okay. Similarly, I can do this for every one of my signals. What is that? It's something that I used to make that finite, right? Oh, yeah, you mean I omitted it here. Yeah, right. Thanks. So that should be there. And similarly, this is tau. The number of instances could be, I mean, that also has to go to infinity. Okay. So for each one, I could calculate the corresponding power spectral density from the definitions I already knew. Okay. Now it turns out that, so let's say you have the time instant t, and or maybe this is t minus tau, and this is t. Okay. So you can take the expectation. I hope all of you know what this means. This is averaging over the ensemble weighted by the joint probability distribution. X of t, x of t minus tau. Okay. This, for a random process, this is also called the autocorrelation function. Okay. So this is the I am using uppercase X just to denote the whole process. Okay. So even if you don't understand this because you have not heard of these expectations of these things, it's fine. We'll still be able to calculate what we want to. Okay. First of all, what is this for time shift of 0? What is this quantity? It's the variance. Anyway, the mean also can be done, but we are taking only zero mean processes, so I won't even bother with that. So Rx of 0 is the variance. Okay. So now there is a theorem that says that for ergodic processes, basically this autocorrelation function of the random process is the same as the autocorrelation functions you calculate for individual processes. Okay. And the Fourier transform of this is also called power spectral density. Now the reason is obvious because you get the same answer as if you calculate the power spectral density from the individual signals. Okay. So the bottom line is you can calculate the mean square value there. That will be the same as the variance and so on. Okay. So the variance at any time instant is the same as the mean square value of the individual signals. So the variance is the power. Okay. So now what can we do? We know how to calculate the power spectral density. We know the normal circuit analysis, right? So we have relationships between power spectral densities. From that we can calculate the power, which is the mean squared value, and that is the same as the variance, which is what we had to calculate for the random process, right? So we'll continue from there.